In 5.1, we talked about the standard normal distribution, and that second note in that particular section focused solely on how to calculate with the standard normal distribution and the chart. What we're going to do in 5.2 and 5.3 is find probabilities and find particular values for just normal distributions, right? Ones that are symmetric, they're bell-shaped, they have an area of 1 underneath them, but they may have means that aren't 0, or they may have standard deviations that aren't equal to 1. Right, so that's what this little blurb right here is talking about. We're going to look at just normal distributions where mu may not equal 1 and or sigma may not equal, mu may not equal 0 and or sigma may not equal 1. So to do this, what we have to do is essentially take our score that we're looking at in terms of x's and find its z-score. Once we convert a value into its z-score, then we can use the tables like we did in 5.1. That's going to cover the 5.2 material. For the 5.3, we're going to be going from probabilities to then asking for what value gives us that probability. So for instance, we're going to be looking at finding quartiles and percentiles, and the pth percentile is a value such that p% of the observations fall at or below that value. So the quartile, the first quartile, would be the 25th percentile, if that makes sense. All right, we'll see that in a second. So we want to find the 7th percentile for a standard normal distribution, right? Key here is standard. Since it's standard, we can use our z-chart. In symbols, we're looking for the x value for which 0.07 is the probability that we get. Now, if we go into our chart and we look for 0.07, all right, because that is less than 0.5, we're going to be looking in the negative chart, but there's not going to be a 0.07. The closest we're going to get is 0.0694, which is the value that we're going to be looking at. So that's roughly about 0.07. And if you find 0.0694 in the chart, right, that's going to be in the negative 1.4 row and the 0.08 column. That is the z-score here that matches up with 0.0694. And so what we do to take away from this is this 7th percentile is roughly going to be anything this below this negative 1.48 z-score. Standardized exams are really great examples of how to use z-charts. So the ACT scores are approximately normal with a mean of 21. So in symbols, that's a mean of 21 and a standard deviation of 4.7. So we want to find the probability that a student chosen at random receives less than a 26 on the ACT. First, we're going to convert 26 into its z-score. So z is equal to 26 minus 21 over 4.7. Right, and so the z-score is going to be 1.06, roughly. Now, if you think about the z-chart, it has 2 decimal places. So your z-score should always have 2 decimal places so that you can look at the z-chart to find that number. Next, we want the probability that x is less than 26. What we're doing with the z-score is we're converting it from x to now a z-score. So we're looking really for the probability that z is less than 1.06. So we go into our chart, it's positive, right? So we're on the positive chart. We go to 1.0 and then the column of 0.06. And we find where those two, that row and that column meet. And that gives us 0.8554. Throughout these notes, before we actually calculate the number, just for practice, you should pause the video, find the value here, write it down, and make sure that it matches with what we're going to have as the final answer, just to make sure that you're getting and reading these charts correctly. So the next part is, what is the probability that a student chosen at random receives at least a 24 on the ACT? So again, first step, instead of dealing with 24, what we're going to do is find its z-score. We take the value minus the mean over the standard deviation, and we take 2 decimal places, right? So we get 0.64. Then we want at least a 24, which the probability of x being greater than or equal to 24. We know what the z-score of 24 is, so we're really looking for the probability that z is greater than or equal to 0.64. But remember, our table tells us less than values. It tells us stuff to the left. This is asking for stuff to the right. And so to find stuff to the right, we have to do 1 minus the stuff to the left. All right, and then we go into the chart and we find the appropriate value, and we end up getting that this is 1 minus 0.7389, which gives us 0.2611. So the probability that somebody chosen at random receives at least a 24 on the ACT is about 26%. Next, we want to find the third quartile. So what we're looking for is the probability that x is less than y is equal to 0.75. So I'm using y as the score on the ACT, which represents the third quartile. And we're using 0.75 because, again, the third quartile is the median of the upper half of the data set, and the upper half of the data set's median is 75% of the information. All right, so if you look at your chart, 0.75 is greater than 0.5, so we're looking at the positive chart. But there's not going to be a 0.75 anywhere. The closest we'll be able to get is 0.7486. And we're just going to have to use that because our chart has 2 decimal places for the z-scores. If it went to, say, 4 decimal places, we might be getting more exact answers, but those charts would be huge. Now, where we found this 0.7486, that corresponded to a z-score of 0.67. Right. So we know that the probability that your ACT score is less than this y value equals 0.75 is going to occur when the z-score of your x value is 0.67. Or so our y value is actually 0.67. So we are going to reverse the calculation of z-scores. So we take y minus 21 over 4.7, and that's going to equal 0.67, right? We don't know what our y value is, but we know that our z-score needs to be 0.67 for it to be the third quartile. You multiply both sides by 4.7, you get y minus 21 equals 3.149. Then you add 21 over, and we end up getting y equals 24.149. This is the score for the third quartile. And then likewise, the 80th percentile, we're going to set it up very similarly. We have the probability that x is less than y is equal to 0.8. So if you go into your chart, you're not going to find 0.8, but if you search around, the closest we can get is 0.7995. And that happened at z equals 0.84. And so, just like we did in the last one, we have y minus 21 over 4.7 has to equal 0.84. Multiplying 4.7 on both sides. And then adding 21 gives us y equals 24.948. Right, and there's not a lot of discrepancy between the third quartile and the 80th percentile, because the third quartile is the 75th percentile. And so the 75th percentile and the 80th percentile aren't that far off. And so the scores shouldn't be that far off either. And if you're young enough to remember these things called cassette decks, let's just say that there was a brand of cassette decks that had a deck life that was normally distributed with a mean of 2.3 years. Right, so mu equals 2.3 and a standard deviation of 0.4. So sigma equals 0.4. We're first asked to find what is the probability that the cassette deck will break down less than 1 year after purchase. Right, so the probability that x is less than 1. And we're going to do this just like we did in the last example, except we're going to shorten the notation down a bit. So we have the probability that x is less than 1. We have to convert this into a z-score. So we do z less than, and then we take 1 minus 2.3 over 0.4. Right. This is essentially the calculation we started part 1 or part 2 of the previous example with. We're just doing it in line with everything else now. So if you do that calculation, we get z is less than negative 3.25, which if you go into your chart and you find negative 3.25, you end up getting 0.0006. Right, so the probability that your cassette deck will break down less than 1 year after purchasing it, if the mean is 2.3 years, is fairly low. Right, so there's a very low likelihood that your cassette deck will break down after 1 year. Next, we want to figure out what is the probability that the cassette deck will last for at least 3 years after purchase. So again, we want the probability that x, which is again the random variable keeping track of how long you've had this tape deck, is greater than 3 years. First, we're going to take our x value, convert it to a z-score. So we have 3 minus 2.3 over 0.4, which gives us 1.75. And now, because we're looking for greater than, which is to the right in the area picture, our z-chart only tells us area to the left. So when you have a right, you have to switch it to a left statement. You do the 1 minus, essentially the left statement. So we're looking for the 1 minus the probability that z is less than 1.75. Going into our chart, finding 1.75, you end up getting that is 0.9599. And if you do that subtraction, you get 0.0401. All right, so there's about a 4% likelihood that this cassette deck is going to last at least 3 years. Next, we want to find the 99th percentile for the life of these cassette decks. Right, so when we're setting up the percentile, we always use this placeholder y. That's equal to 0.99. Closest number we can get for 0.99 inside the chart because this number is outside. The closest thing on the inside of the chart is 0.9901, which that has a z-score of 2.33. And just like we did at the end of the previous example, part 3 and 4, when we talked about quartiles and percentiles, we now have to solve for y. So we have y minus 2.3, right, the mean, over 0.4, the standard deviation, equals 2.33. Multiplying both sides by 0.4 gives us y minus 2.3 equals 0.932. And then adding the 2.3 over, we end up getting y equals 3.232. Right, so that is the 99th percentile, which means that by 3.23 years, about 99% of these cassette decks have broken down.